Okay, so in the previous two lectures, we learned that if a group is cyclic, then either that group is isomorphic to the integers under addition if the group has infinite order, or the group is isomorphic to the integers modulo n under addition modulo n if the group has finite order n. Now, we also learned that a cyclic group is a special case of a finitely generated group, and that every cyclic group is abelian. In other words, a cyclic group is a special case of a finitely generated abelian group. And we have a characterization for all cyclic groups up to isomorphism. In other words, there is only one abstract cyclic group of infinite order. The quintessential model for that group is the integers under addition. And there is only one abstract cyclic group of finite order n. The quintessential model for that group is the integers modulo n under addition modulo n. So now we will begin to develop the tools which will allow us to characterize all finitely generated abelian groups, and these tools culminate in what is known as the fundamental theorem of finitely generated abelian groups. So first, we will look at the last exercise from the previous lecture. We will show that the group of quaternion units is generated by the set S, which contains the elements I and J. So proof. Notice that 1 can be represented as the product I squared times J squared. Negative 1 can be represented as the product I squared times J to the 0th power. I can be represented as the product I to the first power times J to the 0th power. Negative I can be represented as the product I to the first power times J to the second power. The element J can be represented as the product I to the 0th power times J to the first power. Negative J can be represented as the product I to the second power times J to the first power. K can be represented as the product I to the first power times J to the first power. And negative K can be represented as the product I to the third power times J to the first power. So for every element Q in the group of quaternion units, there exist integers m and n such that that element is the product I to the power of m times j to the power of n, and hence the group of quaternion units is generated by the set S, consisting of the elements I and j. So let's quickly look at a Cayley digraph for this group with the generating set S. Now, in this digraph, we will denote an edge representing multiplication on the right by I with a solid line, and we will represent an edge representing multiplication on the right by J by a dotted line. So let's start with the identity 1. 1 times I gives us I. I times I is I squared, which is negative 1. Negative 1 times I is negative I. And negative I times I is 1. Now, 1 times j gives us j. Now j times I gives us negative k. Negative k times I gives us negative j. Negative j times I gives us k. And k times I gives us j. Now I times j gives us k. Negative 1 times j gives us negative j. And negative I times j gives us negative k. Now negative k times j gives us I. J times j gives us negative 1. K times j gives us negative I. And negative j times j gives us 1. So here is a representation of the digraph, Cayley digraph, for the quaternion units with the generating set I and j. So notice that the group of quaternion units is finitely generated, but is not abelian. So as an exercise, let G be a group where the order of that group is less than or equal to 4. Prove that the group is abelian. And as a third exercise, let G be a group of order 4. Prove that either G is isomorphic to the integers modulo 4, or G is isomorphic to the Klein-Fear group. Okay, so new definition. Let x sub 1 through x sub n be a finite collection of sets. The finite Cartesian product of these sets is the set which we denote this way: a large letter pi with the indices I equals 1 to n of the sets x sub I. Again, this is the finite Cartesian product, x sub 1 cross x sub 2, and so on through x sub n, which is the set of all ordered n tuples, x sub 1 through x sub n, where the ith coordinate, x sub I, is an element in the set x sub I. That is the Cartesian product of a finite collection of sets consists of all ordered n tuples, which I will denote using vector notation, where the ith coordinate x sub I of the ordered n-tuple is an element in the set x sub I, which is the ith factor of the Cartesian product. So let's look at an example to clarify the definition. So let the set X be the Cartesian product of the integers with the rationals with the reals. Then the set X consists of all ordered triples x sub 1, x sub 2, and x sub 3, where the first coordinate, x sub 1, is an element in the set of integers. The second coordinate, x sub 2, is an element in the set of rationals. And the third coordinate, x sub 3, is an element in the set of reals. Now the set of integers is the first factor. The set of rationals is the second factor. And the set of reals is the third factor of the Cartesian product. Now the order of the factors matters if y is the Cartesian product of the rationals with the integers with the reals. Then we still have the same factors, but the order is now different. Then the Cartesian product y is not equal to the Cartesian product x, since the ordered pair 1/2, 1 and 0, is an element in the Cartesian product y, and this ordered triple 1/2, 1, 0 is not an ordered triple in the Cartesian product x. Okay, so new definition. Let G sub 1 through G sub n be a finite collection of groups. The external direct product of these groups is a Cartesian product of these groups together with a binary operation defined as follows. For every pair of ordered intuples A and B in the Cartesian product of the groups, we have that the product A times B is the product of the ordered intuples A sub 1 through A sub n and B sub 1 through B sub n, which is the ordered intuple whose elements or coordinates are A sub 1 times B sub 1 and so on through A sub n times B sub n. That is, the product is defined component-wise. Now, in this definition, we are using the language and notation of a multiplicative group, or a finite set of multiplicative groups. But this definition holds for additive groups as well. So let's look at an example. Let G be the Cartesian product of the integers modulo 2 under addition with the group of integers modulo 3 under addition modulo 3. Then, for every two ordered pairs in this Cartesian product, we have that the sum of the two elements is the sum of the ordered pairs A1, A sub 2, and B sub 1, B sub 2. And this is the ordered pair whose first coordinate is A sub 1 plus B sub 1 modulo 2, and whose second coordinate is A sub 2 plus B sub 2 modulo 3. So for example, if we add the ordered pair 1, 1 with itself, then this is the ordered pair whose first coordinate is 1 plus 1 modulo 2, and whose second coordinate is 1 plus 1 modulo 3, and this is the ordered pair 0, 2. Okay, so now we'll prove a theorem. Again, let G sub 1 through G sub n be a finite collection of groups their direct product is itself a group of order the product of the orders of the factor groups.